Here is what nobody tells you about the cold of deep space. It does not freeze you. Not instantly. Not the way every science fiction movie has shown you. An unprotected human body drifting in the void between stars would stay warm for hours because there is almost nothing out there to pull the heat away. No air, no water, no wind. Just emptiness so complete that your own body heat has nowhere to go except slowly, invisibly, as infrared radiation bleeding into the dark. And that is what makes deep space so much more dangerous than you imagine. The real horror is not freezing. It is the fact that every spacecraft, every habitat, every living system must fight an invisible war against thermal chaos with zero margin for error. If this kind of deep science exploration interests you, consider hitting that like button and subscribing. I appreciate every single one of you that continues to support the channel. Now, get yourself comfortable. Let's begin. You already know what happens when a helmet cracks in space. You have seen it 100 times. The visor shatters, the air screams outward, and the astronaut's face freezes solid in less than a second. Ice crystals race across exposed skin, eyes frost over. The body becomes a rigid sculpture drifting through the void, locked in whatever expression it wore at the moment of death. This image lives in your mind because Hollywood put it there. Dozens of films have taught you that space is the coldest, most immediately lethal environment imaginable, a place where exposed flesh freezes faster than liquid nitrogen can manage on Earth. The assumption feels intuitive. Space is cold. Therefore, space freezes things. Instantly. It does not. That single correction changes everything about how you should understand surviving beyond Earth's atmosphere. And the reality that replaces the myth is far more unsettling than any movie has ever shown you. Because the true thermal danger of space is not a fast killer. It is a slow, invisible, relentless one that engineers must fight every second of every mission. To understand why space does not flash freeze anything, you need to understand how heat actually moves. On Earth, heat travels through 3 mechanisms. The first is conduction, the direct transfer of thermal energy through physical contact. Touch a metal railing on a winter morning, and heat flows out of your hand into the cold steel. The atoms in your skin vibrate against the atoms in the metal, passing kinetic energy from warmer material to cooler material. This is why a tile floor feels colder than a wooden floor at the same temperature. The tile conducts your heat away faster. The second mechanism is convection, the movement of heat through a fluid, meaning a liquid or a gas. When you step outside into freezing wind, that wind carries your body heat away because moving air molecules collide with your skin, absorb energy, and are immediately replaced by fresh, cold molecules rushing in behind them. Wind chill exists because convection is extraordinarily efficient at stripping heat from warm objects. The faster the air moves, the faster you cool. Jump into an icy lake, and convection becomes even more savage, because water conducts heat roughly 25 times more efficiently than air. A person immersed in near-freezing water can become hypothermic in minutes. The third mechanism is radiation, the emission of electromagnetic energy in the form of infrared light. Every object above absolute zero radiates some heat as invisible light. Your body does this constantly, glowing faintly in the infrared whether you are indoors or outdoors, whether you are surrounded by atmosphere or floating in a vacuum. Here is the critical distinction that demolishes the freezing myth. Conduction requires physical contact between materials. Convection requires a surrounding fluid, either gas or liquid. Space has neither. There is no air in the void between planets. There is no water. There is no gas of any kind in meaningful quantities. The density of particles in interplanetary space is roughly 1 to 10 atoms per cubic centimeter. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. When you remove atmosphere entirely, you eliminate the 2 fastest and most efficient methods of heat transfer that humans have ever experienced. The only mechanism left is radiation. And radiation, when it is your sole means of losing heat, is remarkably slow. Consider what happens to your body on a bitterly cold winter day with strong wind. Your skin temperature can drop several degrees within minutes because convective wind chill is pulling heat away at a ferocious rate. Frostbite can develop on exposed fingers within 5 to 10 minutes in severe conditions. Your body is losing heat to the surrounding air through billions upon billions of molecular collisions every second, each one carrying a tiny packet of energy away from your skin. Now remove all of that air. Remove every molecule surrounding your body. In the vacuum of space, your skin has nothing to collide with. No molecules are carrying your heat away. No wind is replacing warm boundary layers with cold ones. The only energy leaving your body is the infrared radiation streaming off your skin at the speed of light, and the total power of that radiation from an average human body at normal skin temperature is only about 100 watts. That is roughly the output of a single old-fashioned incandescent light bulb. 100 watts is not nearly enough to cool a 70-kilogram mass of warm tissue and circulating blood in any hurry. In fact, calculations based on the Stefan Boltzmann law of thermal radiation show that it would take hours for an unprotected human body in deep space to cool significantly through radiation alone. You would die long before you froze. Oxygen deprivation would claim consciousness in roughly 10 to 15 seconds as dissolved oxygen in your blood was consumed without replenishment. Full death from asphyxiation and circulatory failure would follow within approximately 90 seconds to 2 minutes. Your body would swell as gases dissolved in tissues expanded in the absence of external pressure. Moisture on your tongue and in your airways would begin to boil, not from heat but from the near total absence of atmospheric pressure, which drops the boiling point of water so dramatically that it vaporizes at body temperature. Evaporative cooling from that boiling moisture would chill your mouth and respiratory surfaces rapidly, perhaps to near freezing in those local areas. But your core body temperature, the thermal energy stored in 70 kilograms of warm tissue and several liters of blood, would barely budge. The freezing would come later, gradually, over hours and hours, as radiation slowly bled your remaining thermal energy into the void. You would be long dead and still warm. This is not speculation, we have direct evidence. In 1966, a NASA technician named Jim LeBlanc was testing a prototype spacesuit inside a vacuum chamber at what is now the Johnson Space Center in Houston, Texas. During the test, a pressurization hose connected to his suit became disconnected, causing rapid depressurization. Within seconds, the pressure inside his suit plummeted to near vacuum levels. LeBlanc later recalled that the last thing he felt before losing consciousness was the sensation of saliva boiling on his tongue, a textbook symptom of ebulism in a low-pressure environment. He was exposed to near-vacuum conditions for approximately 14 seconds before technicians were able to repressurize the chamber and restore atmospheric pressure. LeBlanc survived. He regained consciousness almost immediately after pressure was restored. He reported no lasting injuries. He suffered no frostbite, no frozen tissue, no ice crystal damage anywhere on his skin or in his eyes. His body had not frozen even slightly during those 14 seconds of vacuum exposure. The reason is exactly what the physics predicts. There was almost nothing surrounding him to conduct or convect his heat away. The only heat loss was through radiation, and 14 seconds of radiative cooling at approximately 100 watts removes a negligible amount of thermal energy from a human body that stores the equivalent of thousands of watt-hours of heat in its warm mass. The Soyuz 11 tragedy of 1971 provides a far more somber data point. 3 cosmonauts, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev, died when a pressure equalization valve opened prematurely during re-entry preparation, venting their capsule's entire atmosphere into space at an altitude of roughly 168 kilometers. The crew was exposed to vacuum for approximately 11.5 minutes before the capsule re-entered Earth's atmosphere. The recovery team found all 3 dead. The cause of death, confirmed by Soviet medical investigators, was asphyxiation and the effects of depressurization, including hemorrhaging and gas embolism. But the bodies had not frozen. More than 11 minutes of direct vacuum exposure in the cold of space, and temperature was not what killed them. Pressure loss and oxygen deprivation ended their lives while their bodies were still warm. These incidents reveal something that contradicts nearly everything popular culture has taught us about the space environment. Vacuum is lethal, terrifyingly and swiftly so, but it does not kill through cold. It kills through the loss of pressure and breathable atmosphere. The thermal danger is real, absolutely real, but it operates on a completely different timescale than the instant death scenarios movies have burned into our imagination. And this distinction matters enormously for understanding why deep space is actually dangerous, because the true thermal threat is not the speed of freezing. It is the inescapable difficulty of managing heat in a place where the normal rules of heat transfer no longer apply. So if space does not freeze things instantly, what temperature actually is space? This question sounds simple enough. The answer shatters most people's intuition. Space, strictly speaking, does not have a temperature in the way that air or water does. Temperature is a property of matter, a measure of the average kinetic energy of atoms and molecules in a substance. A vacuum contains essentially no matter. Asking what temperature a vacuum is resembles asking how much a shadow weighs. The concept does not meaningfully apply to the thing being described. What space does have is a radiation environment, a bath of photons that fills every cubic centimeter of the observable universe. The dominant component of this bath is the cosmic microwave background, the faint afterglow of the Big Bang, an almost perfectly uniform field of microwave radiation that has been cooling for approximately 13.8 billion years as the universe expanded. Today, that radiation corresponds to a blackbody temperature of approximately 2.725 Kelvin. That is roughly minus 270 degrees Celsius, or approximately minus 455 degrees Fahrenheit, just 2.7 degrees above absolute zero, the lowest temperature that physics allows. This radiation arrives from every direction with astonishing uniformity, varying by only a few millionths of a degree from one patch of sky to another. It is the coldest natural thermal environment that exists anywhere in the known universe. But here is what most people misunderstand about that number, 2.725. Kelvin is not a temperature that space imposes on objects the way a freezer imposes its temperature on food. It is the temperature a perfectly absorbing object would eventually reach if placed in deep interstellar space, far from any star, with no internal heat source, and left alone for long enough to come into thermal equilibrium with the cosmic microwave background. That process, depending on the object's mass, insulation, and surface properties, could take hours, days, or even weeks. The cosmic microwave background does not grab heat out of objects the way cold water does. It does not blow across a spacecraft like an Arctic gale. It simply exists as a faint, omnidirectional bath of extremely low-energy photons, and an object in space will radiate its own heat away, photon by photon, until its temperature drops low enough that the energy it emits matches the energy it absorbs from this background. The background is the floor, not the force, and reaching that floor takes far longer than most people imagine. The actual temperature of any real object in space depends on a balance of energy inputs and outputs that has almost nothing to do with the background temperature of the void. There are three factors that determine how hot or cold something gets. The first is absorbed sunlight. Any object within a star system receives electromagnetic radiation from its host star, and the amount depends on distance, orientation, and surface properties. A spacecraft in Earth orbit, at a distance of 1 astronomical unit from the Sun, absorbs roughly 1,360 watts of solar energy per square meter of sunlit surface. That is a substantial amount of heating, comparable to having a small electric space heater running on every square meter of sun-facing hull. The second factor is emitted infrared radiation. Every object above absolute zero radiates heat as infrared light, and the total power emitted depends on both temperature and surface emissivity. The relationship is precise and merciless. Radiated power is proportional to the fourth power of the object's absolute temperature. Double an object's temperature, and the energy it radiates increases by a factor of 16. This means hot objects shed heat much faster than cool ones, and cooling slows dramatically as an object approaches equilibrium. The third factor is internal heat generation. Electronics waste heat, chemical reactions, biological metabolism, radioactive decay, friction in mechanical joints. All of these produce thermal energy inside a spacecraft or a living body, and that energy must be managed. The actual temperature of an object in space is whatever value balances these three factors at any given moment. Absorb more energy than you emit, and you heat up. Emit more than you absorb, and you cool down. Reach equilibrium, and your temperature stabilizes at whatever point makes absorbed and emitted power equal. This is profoundly different from the thermal experience of any living creature on Earth. On our planet, we are surrounded by air that conducts and convects heat so efficiently that our thermal experience is dominated by atmospheric conditions. We feel cold when the air is cold. We feel hot when the air is hot. In space, there is no air to feel. Your temperature is determined entirely by the radiation balance between your surface and every object in your line of sight, from the blazing sun to the frigid void to the warm hull of your own spacecraft. And that balance can produce results that seem physically impossible by earthly standards. The Moon provides the most dramatic natural demonstration of this physics anywhere in the inner solar system. It orbits Earth at roughly the same distance from the Sun, receiving the same solar intensity, yet its surface experiences thermal extremes that dwarf anything on our planet. The reason is simple. The Moon has no atmosphere. No air surrounds its surface to buffer, distribute, or moderate the thermal energy pouring in from the Sun. Every square meter of lunar regolith is on its own, absorbing sunlight when illuminated and radiating heat into the void when shadowed, with nothing in between to soften the transition. The results are staggering. During the roughly 14 Earth day lunar daytime, surface temperatures in equatorial regions climb to approximately 127 degrees Celsius. That is hot enough to boil water at sea level pressure. Hot enough that the Apollo astronauts reported feeling the heat radiating upward through the soles of their boots, even through multiple layers of insulation. Then the 2-week lunar night descends. Without atmosphere to retain even a fraction of the daytime warmth, surface temperatures plummet to approximately minus 173 degrees Celsius within hours. The same patch of ground that was hot enough to boil water at noon becomes cold enough to liquefy oxygen by midnight. A thermal swing of roughly 300 degrees Celsius happening on the same spot, driven by nothing more than whether the sun is above the horizon or not. But the most striking thermal environments on the Moon are not on its sun-baked equatorial plains. They are in the permanently shadowed craters near the lunar poles. These are regions at the bottom of deep impact craters whose rims are tall enough that direct sunlight has not touched their floors for billions of years. With no atmosphere to scatter light or carry warmth from nearby sunlit areas, these crater floors exist in perpetual darkness, their only thermal input being the faint cosmic microwave background and the tiny amount of infrared radiation emitted by crater walls that occasionally catch a sliver of reflected sunlight from distant ridges. NASA's Lunar Reconnaissance Orbiter, using its Diviner thermal radiometer, measured temperatures inside some of these permanently shadowed craters at approximately minus 248 degrees Celsius. That is roughly 25 Kelvin, colder than the surface of Pluto, colder than any natural environment measured anywhere else in the inner solar system, and only about 25 degrees above absolute zero. Craters like Shackleton and others near the lunar South Pole contain pockets of cold so extreme that they function as natural cryogenic traps, cold enough to capture and hold water ice, frozen carbon dioxide, and other volatile compounds that would sublimate instantly on any sunlit surface. These are among the coldest naturally occurring temperatures ever measured by any spacecraft instrument in our solar system, and they exist on a body orbiting less than 400,000 kilometers from Earth. The Moon is a world-sized demonstration of what happens when radiation is the only mechanism for thermal exchange. There is no air to equalize temperatures between sunlit and shadowed terrain. There is no wind to carry heat from warm regions to cold ones. There is no ocean to moderate seasonal swings. Every surface is thermally isolated from every other surface except through the agonizingly slow conduction of heat through rock and dust. The result is a landscape where lethal heat and lethal cold exist within meters of each other, separated by nothing more than the angle of a crater wall or the shadow of a boulder. An astronaut standing in direct equatorial sunlight on the Moon is being heated to temperatures above boiling, while the shadowed ground behind a nearby rock lies below minus 150 degrees Celsius. Both conditions exist simultaneously in the same location on the same world. The only difference is geometry. Where the photons land, it is blisteringly hot. Where they do not, it is savagely cold, and nothing in the environment bridges the gap. This is the same physics that governs every spacecraft in orbit, every space station, every probe, and every habitat that humanity has ever launched. The Moon simply makes it visible on a planetary scale, written across its surface in temperature gradients so extreme they would be physically impossible anywhere on Earth. Consider the International Space Station. This single interconnected structure orbits Earth at an altitude of roughly 400 kilometers. It completes one orbit every approximately 90 minutes, spending about 45 minutes in direct sunlight and 45 minutes in Earth's shadow during each pass. The temperature difference between these two phases is staggering. External surfaces exposed to direct sunlight can reach approximately 121 degrees Celsius, well above the boiling point of water and hot enough to cause immediate burns on contact. The same surfaces, when they rotate into Earth's shadow just minutes later, can plunge to approximately minus 157 degrees Celsius, cold enough to make steel dangerously brittle and to freeze most organic compounds solid. That is a swing of nearly 280 degrees Celsius happening on the same piece of hardware, on the same orbit, roughly 16 times per day. Think about what this means. The station is not traveling between different regions of space. It is not moving closer to or farther from the sun in any meaningful sense. It is orbiting at a constant altitude, and the only thing changing is whether direct sunlight happens to be hitting a given surface at that moment or not. One face of the station bakes, the opposite face freezes. Both extremes exist simultaneously, separated by nothing more than the geometry of solar exposure. A bolt on the sunlit face of a solar panel array might be hot enough to blister bare skin, while a bolt on the shadowed face of the same truss segment is cold enough to fracture if struck sharply. This thermal reality, this constant war between broiling heat on one side and savage cold on the other, is the defining feature of the space environment, and it is fundamentally different from any cold that exists on Earth. In Antarctica, the coldest continent on our planet, temperatures at the highest research stations can drop below minus 89 degrees Celsius. That is brutally, profoundly cold. But it is uniform. The air surrounding you is cold. The ice beneath your feet is cold. The wind striking your face is cold. Every direction offers the same thermal message, and the survival strategy is conceptually simple. Insulate yourself. Generate heat. Shelter from the wind. Wait for conditions to improve. The cold is an enemy, but it is a predictable one that attacks from every direction equally. In space, the problem is categorically different. The problem is not that everything around you is cold. The problem is that nothing around you is anything. There is no medium surrounding you at all. On one side, relentless solar radiation pours roughly 1,360 watts onto every square meter of exposed surface, actively heating the structure. On the other side, the void offers a radiation sink just a few degrees above absolute zero, pulling heat away through infrared emission. And sandwiched between these two extremes, the spacecraft itself is generating internal waste heat from electronics, life support, crew metabolism, and power systems, heat that has nowhere to go except through radiation into either the blazing sunlight or the freezing dark. Managing this three-way thermal tug-of-war is not optional. It is the single most critical engineering challenge of keeping anything alive in orbit. And this is why the popular understanding of space as simply cold is not merely incomplete. It is dangerously misleading. A spacecraft engineer who treated space as nothing more than a cold environment and simply piled on insulation would build a vehicle that overheated and failed within hours. The International Space Station devotes more engineering tonnage and complexity to getting rid of excess heat than to staying warm. Its external cooling system pumps toxic ammonia coolant through enormous radiator panels that face the cold sky, rejecting tens of kilowatts of waste heat as infrared radiation. Without that system running continuously, the combined metabolic heat of 6 crew members, plus the waste heat from hundreds of computers, experiments, life support processors, communication systems, and power distribution electronics, would raise the station's internal temperature past survivable limits within a matter of hours. The crew would not freeze, they would cook, inside a spacecraft orbiting in what everyone casually calls the cold of space. The paradox sharpens when you realize that both thermal dangers, overheating and freezing, exist simultaneously in the same vehicle on the same orbit. Sunlit radiator panels reject heat efficiently because they face cold space. But if a station maneuver or attitude change causes those panels to face the sun instead of empty sky, they absorb solar energy rather than rejecting waste heat, and the cooling system's effectiveness drops sharply. Meanwhile, sections of the station permanently in shadow, or components with poor thermal coupling to the heated interior must rely on electric heaters powered by the solar arrays to prevent water lines from freezing, propellant from solidifying, and sensitive instruments from dropping below their minimum survival temperatures. The station fights overheating in some compartments while battling freezing in others, on the same orbit, around the clock, and the only thing preventing both extremes from causing catastrophic failures is a network of coolant loops, heaters, radiators, thermal coatings, insulation blankets, louvers, and computerized controllers working continuously to shuttle heat from where it is unwanted to where it is needed. This is the reality that the instant freezing myth hides from view. Space does not attack you with cold the way a blizzard does. Space does not attack you at all. Space simply removes every environmental convenience that makes thermal survival manageable on Earth. It strips away the air that carries heat from your furnace to your living room. It eliminates the water that absorbs excess warmth from your skin on a summer day. It erases the atmosphere that softens the temperature difference between noon and midnight. What it leaves behind is a radiation-only universe where every thermal interaction is governed by the slow, invisible exchange of infrared photons between surfaces, and where the margin between a livable interior and a dead spacecraft depends entirely on whether you can manage that exchange precisely enough to keep every component, every fluid, every biological system within its narrow operating range. And this is just low Earth orbit. This is the comparatively gentle thermal environment where the sun is close, powerful, and dependable, where solar panels generate abundant electricity to run heaters and pumps, where the orbital day-night cycle is a predictable 90-minute rhythm that engineers can model and design around with high confidence, where Earth itself provides a significant source of reflected sunlight and infrared warmth that partially offsets the cold of shadow passes. What happens when you leave this neighborhood behind? What happens when you aim outward, past Mars, past the asteroid belt, past Jupiter, past Saturn, into regions of the solar system where the sun shrinks from a blazing disk to a bright point, barely distinguishable from the background stars? What happens when the solar energy that keeps your spacecraft warm drops to less than 4% of what you receive at Earth, then to 1%, then to 0.1%? The thermal machine that keeps a spacecraft alive near Earth depends on a generous and reliable supply of solar energy. Strip that energy away gradually, as the inverse square law does with merciless mathematical precision for every kilometre you travel outward, and the machine must find heat from somewhere else. Or everything aboard, every instrument, every fluid line, every battery, every seal, every living cell, begins the slow, remorseless slide toward the temperature of the void, not instantly, not dramatically, but relentlessly, system by system, component by component, degree by degree, in a process far more terrifying than any flash freeze Hollywood has ever imagined. Every spacecraft ever launched is a thermos bottle, not metaphorically, literally. The same engineering principle that keeps your coffee hot for hours keeps astronauts alive in the void. A thermos works by creating a vacuum layer between two reflective walls. That vacuum eliminates conductive and convective heat loss, and the reflective walls minimize radiative transfer by bouncing infrared energy back toward the warm contents, instead of letting it escape to the cooler exterior. This is the oldest and simplest thermal control technology in spaceflight, and more than 60 years after the first crewed missions, it remains the foundation on which every other thermal system is built. The spacecraft version is called multi-layer insulation. If you have ever seen a satellite being assembled or watched footage of a spacecraft being prepared for launch, you have seen it without necessarily knowing what you are looking at. It is the gold or silver blanket material that covers nearly every surface of every spacecraft, probe, and space telescope ever built. Those shimmering sheets are not decorative. They are the first and most critical line of thermal defense between a spacecraft's delicate interior and the radiation extremes of the space environment. A typical multi-layer insulation blanket consists of 10 to 30 individual layers of thin reflective film, usually aluminized mylar or aluminized kapton, each sheet roughly 1/4 of an inch thick. Between each reflective layer sits a spacer made from a low-conductivity mesh material such as Dacron or Nomex netting. The spacers serve a crucial purpose. They prevent the reflective layers from touching each other directly, because even in a vacuum where convection is impossible, heat can still travel through solid physical contact via conduction. If the layers pressed flat against one another, thermal energy would conduct straight through the stack from the warm inner surface to the cold outer surface, rendering the reflective properties nearly useless. The mesh spacers hold the layers apart, forcing heat to cross tiny gaps where it can only move by radiation, and each reflective layer bounces most of that radiation back. The cumulative effect is astonishing. A well-constructed blanket with 15 to 20 layers can reduce radiative heat transfer by a factor of 50 to 100 compared to an uninsulated surface. The effective emittance, the measure of how freely heat can radiate through the blanket, drops as low as 0.01. That means 99% of the thermal radiation attempting to escape through the insulation is reflected back. But here is the first surprise that catches people off guard. Multi-layer insulation is not designed primarily to keep spacecraft warm. Its purpose is to give engineers control. On the sunlit side of a spacecraft, the insulation blocks incoming solar radiation from overheating the interior. On the shadowed side, it prevents the interior's warmth from bleeding away into the void. The blankets do not choose one job. They do both simultaneously, on different faces of the same vehicle, creating a thermal boundary that slows the flow of radiant energy in both directions. Without this boundary, direct sunlight would drive exposed hull surfaces past 100 degrees Celsius, while shadowed surfaces plummeted far below -100 degrees Celsius, and the spacecraft's interior would be at the mercy of whichever face happened to dominate the thermal balance at that moment. Multi-layer insulation transforms a spacecraft from a naked object buffeted by radiation extremes into a controlled thermal environment where engineers can decide how much heat enters, how much leaves, and where it goes. The construction of these blankets is almost absurdly painstaking, because performance depends critically on how the layers sit in relation to one another. Every blanket must be custom designed and hand-assembled for its specific location on the spacecraft. Seams, folds, and penetrations, places where wiring harnesses pass through or where blankets overlap at structural joints, dramatically reduce insulative performance if not handled carefully. A wrinkle that compresses 3 layers together creates a thermal short circuit at that point, a bridge where heat can leak through by conduction. An unsecured edge that peels back in the thermal cycling of orbit exposes the surface beneath to direct radiative exchange with the environment. Engineers treat these blankets with the same meticulous attention given to flight-critical avionics, because a poorly installed insulation blanket can cause a thermal failure just as surely as a broken heater can. And heaters are the second essential component of the thermal control system. Multi-layer insulation slows heat loss, but it cannot stop it entirely. Even the best blankets leak some thermal energy, and in shadow or at great distances from the sun, that slow leak can eventually drag temperatures below critical thresholds. To counteract this, spacecraft carry electric resistance heaters, small strips or patches bonded directly to the surfaces of components that must stay within specific temperature ranges. A heater on a propellant line keeps hydrazine fuel above its freezing point of roughly 2 degrees Celsius. A heater on a battery pack maintains lithium-ion cells above their minimum operating temperature, typically around -20 degrees Celsius for most spaceflight-rated cells. A heater on an optical instrument prevents the lens housing from contracting enough to distort the optics. These heaters are conceptually simple, just resistive elements that convert electrical current into thermal energy, but their placement and power levels are engineered with extraordinary precision. Every watt spent on heating is a watt not available for science instruments, communications, attitude control, or life support. On a power-limited spacecraft far from the sun, the electrical budget for heaters can become the single largest constraint on mission operations. Engineers do not install heaters generously. They calculate the minimum power required to keep each component above its survival temperature by the narrowest margin they are willing to accept, and they design thermostatic controllers that cycle heaters on and off in tight loops to avoid wasting a single watt more than necessary. But the part of spacecraft thermal engineering that truly defies intuition is not insulation or heating. It is cooling, because the single most dangerous thermal threat to most spacecraft is not freezing, it is overheating. This sounds wrong. It sounds like it cannot possibly be true in an environment where background temperatures hover near absolute zero, but the logic is inescapable once you follow it. Every electronic component aboard a spacecraft generates waste heat when it operates. A computer processor converts electrical energy into computation and waste heat. A communications transmitter converts electrical energy into radio signals and waste heat. In a crewed vehicle, the problem compounds enormously. Each human body generates roughly 80 to 100 watts of metabolic heat continuously, and during exercise that figure can spike to 300 watts or more. 6 crew members at rest produce at least 500 watts of body heat. That heat enters the cabin air, warms the surfaces, raises the temperature. On Earth, all of this waste heat is trivially easy to manage. Open a window, run a fan, turn on an air conditioner that pumps heat from the indoor air into the outdoor air through a refrigerant cycle. Every one of these solutions depends on the existence of a surrounding atmosphere that can absorb and carry away thermal energy through convection. In space, there is no outside air to dump heat into. The only way to move thermal energy from the interior of a spacecraft to the exterior environment is through a carefully designed chain of thermal connections that ultimately terminates at a surface facing the cold void, where the energy is radiated away as infrared light. If any link in that chain breaks, if a pump fails or a fluid line freezes or a radiator is pointed at the wrong patch of sky, the waste heat has nowhere to go. It accumulates. Interior temperatures climb. Electronics begin exceeding their maximum rated temperatures. Components shut down or malfunction. Batteries overheat and risk thermal runaway. In a crewed vehicle, the cabin becomes unbearably hot. Humidity rises as the crew sweats, condensation forms on cooler surfaces, water droplets float freely in microgravity, and the entire environment degrades toward conditions incompatible with human survival. This is why the International Space Station's thermal control system is one of the most sophisticated pieces of engineering ever built. The interior of the station uses a water-based coolant loop. Cold water circulates through rack-mounted cold plates and heat exchangers that absorb waste heat from experiments, computers, life support processors, and cabin air. This warm water flows to an interface heat exchanger where it transfers its thermal energy to the station's external cooling system. The external system uses anhydrous ammonia as its working fluid, chosen because ammonia remains liquid across an enormous temperature range, from roughly minus 77 degrees Celsius to plus 132 degrees Celsius at the pressures used, and because it has excellent thermal capacity, meaning each kilogram of ammonia can absorb and carry a large amount of heat. Mechanical pumps drive the ammonia through loops mounted along the station's truss structure, carrying absorbed heat away from the pressurized modules and out to massive radiator panels that face the cold sky. These radiator panels are the station's thermal exhaust system. They are constructed from aluminum honeycomb panels coated with high emissivity materials designed to radiate infrared energy as efficiently as possible. The total radiator area on the station is enormous. Hundreds of square meters of surface devoted to nothing but dumping heat into space. The panels can rotate on tracking mechanisms to maintain optimal orientation, facing away from the sun and toward the coldest available patch of sky to maximize the temperature difference that drives radiative heat rejection. The ammonia flowing through tubes bonded to the radiator surface arrives warm, transfers its heat to the panel, and radiates that energy into space as infrared photons. The now cooled ammonia flows back into the station to collect more waste heat, completing the cycle. The system operates continuously, around the clock, around the orbit, through every sunlit pass and every shadow pass. Total heat rejection capacity is approximately 70 kilowatts across both independent loops. This is enough to handle the combined thermal output of all the station's electrical systems, all 6 crew members, all active experiments, and the solar energy absorbed by the station's structure during illuminated orbital passes. If even one of the 2 loops fails, as happened during a pump module malfunction that required emergency spacewalks to repair, the station must immediately begin powering down non-essential systems to reduce the internal heat load, because a single loop cannot reject enough energy to keep the entire station within safe temperatures. The ammonia itself poses its own thermal challenge. Ammonia is toxic. A leak in the external cooling loop near a module wall could potentially contaminate the station's atmosphere if ammonia migrated through microfractures or seal interfaces into the pressurized volume. This is why the internal cooling system uses water, a safe and familiar fluid, and the external system uses ammonia, a thermally superior but toxic one, with the interface heat exchanger serving as the critical barrier between the two. If ammonia were ever detected inside the station's cabin atmosphere, the crew would don emergency breathing equipment and begin isolation procedures. The choice of coolant is itself a thermal design trade-off, balancing performance against safety, complexity against reliability, weight against capability. Heat pipes add another layer of thermal management. A heat pipe is an elegantly simple device, a sealed tube containing a small amount of working fluid, often ammonia, acetone, or water, depending on the temperature range. One end of the tube is heated. The fluid at that end vaporizes, absorbing thermal energy. The vapor travels through the tube to the cooler end, where it condenses, releasing its stored heat. The condensed liquid then returns to the hot end through a wick structure lining the tube's inner wall, driven by capillary action rather than mechanical pumping. No moving parts, no power required. Just physics exploiting the phase change between liquid and vapor to transport heat from one location to another with remarkable efficiency. Spacecraft use heat pipes extensively to move thermal energy short distances, connecting hot components to radiator surfaces or spreading heat across structural panels to prevent localized hotspots. Variable conductance heat pipes take this concept further. By incorporating a small reservoir of non-condensable gas, engineers can create heat pipes that automatically adjust their thermal conductivity based on temperature. When the heat source is cool, the gas expands into the condenser section, blocking the vapor from reaching the far end of the pipe and reducing heat transfer. When the source warms up, the vapor pressure increases, compressing the gas bubble and opening more of the condenser for heat rejection. The heat pipe self-regulates, providing more cooling when temperatures are high and less cooling when temperatures are low, all without any electronic controller, any sensor, or any power input. It is passive thermal feedback using nothing but the thermodynamic properties of fluids and gases. Thermal louvers offer yet another approach to variable heat rejection. These devices, mounted on radiator surfaces or spacecraft panels, function much like adjustable window blinds. When closed, the louver blades present a low emissivity surface that reflects infrared radiation back toward the spacecraft, minimizing heat loss. When open, the blades rotate to expose a high emissivity surface that radiates heat efficiently into space. The actuation mechanism typically uses bimetallic springs or wax-filled actuators that respond directly to temperature changes, opening the louvers when the underlying surface gets too warm and closing them when it cools. Like variable conductance heat pipes, louvers provide passive self-regulation without requiring electrical power. Thermal coatings complete the passive toolkit. Every exterior surface on a spacecraft is treated with coatings chosen for their specific optical properties, defined by two numbers: solar absorptivity, which describes how much incoming solar energy the surface absorbs, and infrared emissivity, which describes how efficiently the surface radiates heat in the thermal infrared spectrum. A surface with high absorptivity and low emissivity gets very hot in sunlight because it soaks up solar energy but radiates heat away slowly. A surface with low absorptivity and high emissivity stays cool because it reflects most incoming sunlight and efficiently emits whatever heat it does absorb. Engineers select coatings for each surface based on whether that area needs to stay warm, stay cool, or serve as a radiator. White thermal control paints, typically zinc oxide or titanium dioxide based, are common choices for radiator surfaces because they reflect visible sunlight while emitting strongly in the infrared. Gold coatings, like those visible on many satellite components, have low emissivity and are used where heat retention is the priority. The interplay of all these systems, insulation blankets, electric heaters, radiator panels, fluid loops, heat pipes, louvers, and thermal coatings, creates what engineers call the thermal control subsystem. And on any spacecraft, this subsystem is not an afterthought bolted on at the end of the design process. It is one of the first systems designed and one of the last to be finalized, because thermal management touches everything. The physical placement of every electronic box, every fluid line, every structural panel must account for the thermal environment it will experience. Hot components must be mounted where they have conductive paths to radiators. Cold-sensitive components must be located where heater power can reach them efficiently. Fluid lines must be routed to avoid both freezing shadows and overheating sunlit zones. Every wiring harness penetration through an insulation blanket must be sealed and grommeted to prevent thermal leaks. The barbecue roll maneuver reveals just how fundamental thermal management is to basic spacecraft operations. During the Apollo missions to the Moon, engineers discovered that if the spacecraft maintained a fixed orientation during the roughly 3-day coast between Earth and the Moon, the sun-facing side would heat dangerously, while the opposite side cooled to levels that threatened fluid lines and structural integrity. The solution was passive thermal cycling. Controllers commanded the spacecraft to rotate slowly around its long axis at roughly 3 revolutions per hour, like a chicken on a rotisserie spit, ensuring that every surface received roughly equal solar exposure over time. This technique, which the Apollo crews nicknamed the barbecue roll, distributed solar heating evenly enough to keep the vehicle within its thermal limits, without requiring additional heaters or radiators. The barbecue roll was not an elegant solution. It was an admission that even with insulation, heaters, and coatings, the spacecraft could not passively survive the thermal asymmetry of interplanetary space without physically rotating itself to average out the solar input. And it is still used today. Deep space probes, interplanetary cruise stages, and even some satellites use slow roll maneuvers to manage solar heating during transit phases. The geometry of sunlight exposure is that important. Fail to rotate, and one side of your spacecraft bakes while the other freezes. Continue that asymmetry long enough, and structural materials begin to warp from differential thermal expansion. Metal on the hot side expands slightly. Metal on the cold side contracts. The resulting mechanical stress can distort antenna alignment, warp optical benches, crack solder joints on circuit boards, and open gaps in insulation blanket seams that accelerate further thermal degradation. The roll eliminates these asymmetries by turning every surface into the sun and away from it in a continuous slow cycle, never allowing any face to reach its thermal extreme. All of these systems, every blanket, every heater, every radiator, every fluid loop, every coating, every louver, every heat pipe, every maneuver, serve a single purpose. They maintain what engineers call the thermal balance. At any given moment, the total heat entering the spacecraft from all sources, solar absorption, internal generation, heater output, must equal the total heat leaving the spacecraft through all paths: radiator emission, insulation leakage, deliberate venting. If input exceeds output, the vehicle warms. If output exceeds input, it cools. Thermal balance is not a steady state you achieve once and forget. It shifts constantly as the spacecraft's orientation changes, as the sun angle varies, as instruments cycle on and off, as crew activity fluctuates, as shadow passes come and go. The thermal control system must track these changes and adjust continuously, shifting heater power, repositioning louvers, adjusting pump speeds, sometimes commanding attitude maneuvers, all to maintain every component within its qualified temperature range. The margins within this system are narrower than most people would believe comfortable. A typical electronics box on a spacecraft might be qualified for operation between -20 degrees Celsius and +50 degrees Celsius. That sounds like a generous range until you realize that the environmental temperature outside the spacecraft's insulation shell swings from +120 degrees to -160 degrees on a 90-minute cycle. The insulation, heaters, and thermal connections must compress that nearly 300-degree environmental swing into a gentle ripple of perhaps 10 to 20 degrees inside the electronics compartment. One layer of failure, a heater that sticks off, a louver that jams closed, a coolant pump that slows, can push a component outside its range within minutes. Thermal engineers spend years modeling these scenarios before a spacecraft ever leaves the ground. They build detailed computational models containing thousands of individual thermal nodes, each representing a small section of the spacecraft's structure, and calculate the heat flow between every pair of nodes for every conceivable orbital condition: sun angle, power mode, and failure case. These models predict temperatures across the entire vehicle to within a few degrees, and they are validated against physical testing in thermal vacuum chambers on the ground, facilities that simulate the vacuum and radiation environment of space by pumping air out of a large chamber and surrounding the test article with liquid nitrogen-cooled walls that replicate the cold radiation sink of the mine. Void. The spacecraft, or a full-scale thermal model of it, is placed inside, illuminated by solar simulation lamps, and monitored as its temperature distribution stabilizes under simulated orbital conditions. If the measured temperatures match the predictions, the thermal design is considered validated. If they diverge, engineers must identify the discrepancy, whether it is a modeling error, an insulation defect, a heater malfunction, or an unexpected thermal path, and fix it before the vehicle is committed to flight. There is no second chance once a spacecraft is in orbit. No repair crew can add a heater strip to a cold propellant line or patch a torn insulation blanket on a deep space probe. The stakes of this engineering are existential. The Hubble Space Telescope provides a vivid example. During servicing missions in the 1990s, astronauts discovered that the outermost layer of Hubble's multi-layer insulation had degraded severely. The Teflon-based material covering the exterior had become embrittled and cracked after years of exposure to the combined assault of ultraviolet radiation, charged particle bombardment, and relentless thermal cycling. Every 96-minute orbit carried the telescope from sunlight into shadow and back, expanding and contracting, pumping outer insulation layer with each pass. Over thousands of orbits spanning years, this cycling weakened the material at a molecular level. Ultraviolet radiation from the sun broke polymer chains. Energetic electrons and protons from the space environment caused further chemical degradation. The combined damage produced cracks, tears, and peeling across large sections of the telescope's insulation skin. Engineers on the ground had to design replacement insulation patches that astronauts installed during subsequent servicing missions, literally rewrapping sections of the telescope in new thermal blankets while floating in the vacuum of space. Without those repairs, the telescope's interior temperature would have gradually drifted outside the range required for its precision optics and sensitive detectors, degrading or ending one of the most productive scientific instruments in history. Hubble orbits in comparatively gentle conditions, roughly 540 kilometers above Earth, still bathed in substantial solar energy and partially warmed by Earth's own infrared emission and reflected sunlight. Its thermal challenges, while real and demanding, are manageable with the systems described above. The insulation blankets, heaters, thermal coatings, and careful orientation control work together to maintain the telescope's mirrors and instruments within the few degree temperature stability required for astronomical imaging. But every one of these systems depends on assumptions about the thermal environment. They assume a certain minimum level of solar energy input. They assume a certain amount of electrical power available from solar arrays to run heaters and pumps. They assume a thermal cycling pattern of known period and amplitude. They assume that insulation materials will degrade at predicted rates and that heaters will draw predictable currents. What happens when those assumptions are violated? What happens when a spacecraft leaves the inner solar system and the sunlight that powers its entire thermal architecture begins to fade? Not dramatically, not all at once, but steadily, mathematically, according to a law of physics as implacable as gravity itself. A law of physics called the inverse square law dictates that solar intensity drops dramatically with distance. Every thermal assumption built into a spacecraft designed for Earth orbit begins to crumble as the sun recedes, and the machine that keeps you alive must find entirely new sources of heat or watch its margins narrow towards zero in a slow, tightening spiral that no amount of engineering elegance can reverse. Imagine walking away from a campfire on a freezing night. For the first few steps, the heat on your face barely diminishes. You can still feel its warmth radiating against your skin, still see the bright flames lighting the ground around your feet. But you keep walking. 20 paces out, and the fire has shrunk to the size of your fist. The warmth on your face has faded noticeably. You can feel the night air claiming territory that the fire's heat had held at bay. 50 paces, and the campfire is a small bright dot. You feel almost nothing from it. The cold of the surrounding darkness has become your entire thermal reality. 100 paces, and you cannot distinguish the campfire from the background stars. You are alone with the cold. This is precisely what happens to a spacecraft leaving the inner solar system, except the campfire is a thermonuclear furnace, 1.4 million kilometers wide, The freezing night is a void just a few degrees above absolute zero, and the walk stretches not across a field but across billions of kilometers of empty space, where no rescue exists and no warmth awaits. The physics governing this retreat from the sun is described by the inverse square law, one of the most elegant and unforgiving relationships in all of nature. It states that the intensity of radiation from a point source decreases with the square of the distance from that source. Move twice as far from the sun, and you receive not half the sunlight but 1/4, 3 times as far, 1/9, 10 times as far, 1/100th. The decline is not linear, it is geometric and it is merciless. At Earth's orbit, 1 astronomical unit from the sun, a spacecraft receives approximately 1,360 watts of solar energy per square meter of sunlit surface. This is the solar constant, the baseline energy input that every near-Earth thermal design relies upon. It powers solar panels, it warms exterior surfaces, it is the dominant heat source that the entire thermal control system is calibrated around. At 1 astronomical unit, sunlight is generous and dependable. Thermal engineers have ample energy to work with. At Mars, roughly 1.5 astronomical units out, the solar intensity drops to about 600 watts per square meter. Still substantial. Mars rovers and orbiters function well with solar panels, though they must be larger than their Earth orbit counterparts to compensate for the reduced flux. Thermal management remains tractable. Heaters draw more power, but solar arrays can still provide it. At Jupiter, approximately 5.2 astronomical units from the Sun, the picture darkens sharply. Solar intensity has fallen to roughly 50 watts per square meter, less than 4% of what Earth receives. The Juno spacecraft, which entered Jupiter orbit in 2016, became the most distant solar-powered spacecraft ever flown, carrying 3 enormous solar panel wings with a combined area of roughly 60 square meters to capture enough of this feeble sunlight to power its instruments and heaters. Juno represents the practical limit of solar power in the outer solar system. Its panels were specially designed with radiation-resistant solar cells and optimized for the dim light environment. And even so, the mission operated on a fraction of the power budget available to inner solar system missions. Beyond Jupiter, solar panels become essentially useless. The sunlight is simply too weak to generate meaningful electricity, and without electricity, there is no power for the heaters, pumps, and controllers that keep a spacecraft alive. At Saturn, approximately 9.5 astronomical units out, solar intensity drops to roughly 15 watts per square meter. At Uranus, around 19 astronomical units, it falls to approximately 3.5 watts per square meter. At Neptune, roughly 30 astronomical units from the Sun, a spacecraft receives about 1.5 watts per square meter of solar energy. That is roughly 1/900th of what it would receive near Earth. The Sun at Neptune's distance appears as a brilliant point of light, still far brighter than any other star in the sky, but no longer a disk, no longer a source of meaningful warmth. A candle in a cathedral, visible but powerless to heat the space around it. Beyond Neptune, past the orbit of Pluto at roughly 40 astronomical units, and into the Kuiper belt, solar intensity falls below 1 watt per square meter and continues declining. In the interstellar medium, where Voyager 1 now travels at a distance exceeding 160 astronomical units, the Sun delivers less than 1/10,000th of a watt per square meter. At these distances, the Sun contributes essentially nothing to a spacecraft's thermal budget. Whatever heat the vehicle needs must come entirely from within. This is the thermal cliff that every deep space mission must confront, and the only proven technology for providing heat and electrical power beyond the reach of sunlight is the radioisotope thermoelectric generator, a device that converts the heat of radioactive decay directly into electricity. The principle is straightforward. A quantity of radioactive material, typically plutonium-238 in the form of plutonium dioxide, is sealed inside a heavily shielded container. As the plutonium atoms decay, they emit alpha particles that are absorbed by the surrounding material, generating heat. Thermocouples, solid-state devices made from 2 different semiconductor materials bonded together, are arranged around the heat source. One end of each thermocouple contacts the hot plutonium container. The other end contacts a radiator fin exposed to the cold of space. The temperature difference across the thermocouple generates a voltage through the Seebeck effect, producing usable electrical current. The conversion efficiency is low, typically around 6 to 7% for the thermoelectric converters used in spaceflight. This means that for every 100 watts of thermal energy the plutonium produces, only 6 or 7 watts emerge as electricity. The remaining 93 to 94 watts are rejected as waste heat through the generator's external radiator fins. This sounds profoundly wasteful by terrestrial standards, but it is actually a feature, not a flaw, in the thermal economy of a deep space vehicle. That waste heat is not discarded uselessly. Engineers deliberately route it through the spacecraft's structure, using conductive paths and thermal interfaces to distribute radioisotope warmth to components that would otherwise freeze in the sunless void. The generator is simultaneously a power source and a furnace, providing the only thermal energy the spacecraft possesses. The Voyager missions illustrate both the brilliance and the fragility of this approach. Voyager 1 and Voyager 2 launched in 1977, each carrying 3 radioisotope thermoelectric generators loaded with plutonium-238. At launch, each generator produced approximately 158 watts of electrical power, for a combined output of roughly 470 watts per spacecraft. 9 small radioisotope heater units, each producing about 1 watt of thermal energy through plutonium decay without any electrical conversion, were distributed throughout each spacecraft to provide supplemental warming to specific components. That was nearly half a century ago. Plutonium-238 has a half-life of approximately 87.7 years, meaning that after 87.7 years, half of the original atoms will have decayed and the heat output will have dropped by roughly half. After 48 years in space, the Voyager's plutonium fuel has lost a significant fraction of its original thermal output. But the power decline is actually worse than the fuel decay alone would predict, because the thermocouples themselves degrade over time. The semiconductor junctions that convert heat into electricity slowly deteriorate from radiation damage and thermal stress, reducing their conversion efficiency year after year. The combined effect of fuel depletion and thermocouple degradation means each Voyager's electrical output has fallen to approximately 225 watts or less, roughly half the original capacity, and it continues declining by approximately 4 watts per year. 225 watts for an entire spacecraft that is less than the power consumed by a standard household light fixture. And from this shrinking trickle of electricity, the Voyager engineering team must power whatever science instruments remain active, run the spacecraft's attitude control system to keep its antenna pointed at Earth, operate the onboard computers that process commands and format data, drive the communications transmitter that sends data across more than 24 billion kilometers of space, and run whatever heaters are still necessary to keep critical components above their minimum survival temperatures. The thermal consequences of this power starvation have been accumulating for decades. Engineers have progressively shut down heaters on one system after another, accepting that those components will cool to whatever temperature the remaining waste heat and structural conduction can sustain. Instruments that once operated comfortably within their qualified temperature ranges now function in conditions their designers never intended, often well below the minimum temperatures specified in their original engineering documents. And somehow, remarkably, many of them continue to work. The cosmic ray subsystem on Voyager 2 continued returning data even after its dedicated heater was turned off, operating at temperatures significantly below its design flaw. Engineers do not fully understand why some instruments survive so far outside their thermal specifications. Part of the answer may be that qualification temperature ranges include conservative margins, and components in practice can often tolerate colder conditions than their formal ratings indicate. Part of it may be fortunate material properties or forgiving circuit designs, and part of it may simply be luck, the kind of luck that runs out without warning when a solder joint finally cracks from thermal contraction or a capacitor's electrolyte finally freezes solid. The Voyagers are now operating on borrowed time, thermally as well as electrically. Every year, as the generators produce less power and less waste heat, the spacecraft's internal temperatures drop a little further. Components that have been operating near the bottom of their survival range will eventually cross below it. When a critical system fails, whether from cold-induced material fracture, frozen fluid, or electrical malfunction caused by component drift at extreme low temperatures, the spacecraft will lose the ability to maintain Earth contact, orient itself, or process commands. The mission will end not in a dramatic moment, but in a quiet thermal surrender, as the last functioning systems slip below the temperatures they need to survive. New Horizons, the spacecraft that flew past Pluto in 2015 and later visited the Kuiper Belt object Arrokoth, demonstrates a more modern approach to the same fundamental challenge. Its thermal design was built from the start around the knowledge that solar energy would be negligible for most of the mission. The spacecraft carries a single radioisotope thermoelectric generator that produced approximately 245 watts of electrical power at launch. Its internal structure was designed with the avionics and instruments housed inside a thermally insulated core, surrounded by multi-layer insulation blankets. The entire vehicle engineered to trap every available watt of internal warmth. The generator is mounted on a boom extending from the spacecraft body, and roughly 15 watts of its waste heat is deliberately conducted through the boom and structural connections into the insulated core, providing the primary heat source for the entire vehicle. This 15 watts, supplemented by the waste heat from whatever electronics are operating at any given time, is enough to keep the spacecraft's internal temperature above approximately 5 degrees Celsius, safely above the freezing point of its hydrazine propellant. Thermal louvers on the lower deck automatically open or close to regulate this temperature, preventing overheating during early mission phases, when the spacecraft was closer to the sun and its electronics were more heavily loaded, and retaining heat during the cold, quiet coast through the outer solar system. The entire thermal architecture is designed around minimizing heat loss and maximizing the utility of every watt of internally generated warmth. But even with this elegant design, New Horizons faces the same inexorable arithmetic that haunts every deep space vehicle. Its plutonium-238 fuel is decaying, its thermocouples are degrading, its electrical output is falling by roughly 3 to 4 watts per year. As power declines, instruments must be turned off, reducing both the science capability and the internal waste heat that helps warm the spacecraft. The thermal margin narrows, the internal temperature drifts downward. Eventually, the generator will produce too little power to run even a single instrument while maintaining the heater load needed to keep propellant from freezing and electronics from failing. The mission will end when the thermal balance finally tips. The Voyagers and New Horizons are deep space probes, robotic emissaries designed to survive in conditions where no human could follow. But the thermal power death spiral they face is not unique to interstellar distances. It can happen much closer to home, on the surface of another world, where distance from the sun is only part of the problem and the environment itself conspires to make thermal survival progressively harder over time. The Mars exploration rovers, Spirit and Opportunity, provide perhaps the most vivid, real-world example of how thermal fragility can end a mission. Both rovers landed on Mars in January of 2004, designed for 90-day missions on the Martian surface. Mars orbits at roughly 1.5 astronomical units from the Sun, close enough that solar panels remain the primary power source. But Martian nights are long and brutally cold, with surface temperatures dropping below -80 degrees Celsius after sunset and remaining there for roughly 12 hours. No solar panel generates electricity in darkness. Without power, there would be no electricity to run the heaters that kept the rover's electronics and batteries alive through the night. NASA's engineers solved this problem with the same technology that keeps deep space probes warm. Each rover carried 8 small radioisotope heater units, each one containing a tiny pellet of plutonium-238 that produced approximately 1 watt of continuous thermal energy through radioactive decay. 8 watts total. These were not electrical devices. They required no wiring, no power input, and had no moving parts, simply generating heat constantly and reliably as the plutonium decayed. That 8 watts of nuclear warmth, distributed strategically inside each rover's insulated electronics compartment, was enough to keep the most critical components above their minimum survival temperatures through even the coldest Martian nights. Without those 8 tiny plutonium pellets, the rover's batteries would have frozen solid during their first night on Mars. The missions would have ended before they produced a single day of science. Instead, Opportunity explored for nearly 15 years, and Spirit survived for more than 6. But Spirit's eventual death was a thermal story, and it reads like a slow-motion version of the cascade this entire episode has been building toward. Over the years, fine Martian dust accumulated on Spirit's solar panels, gradually reducing their power output. The rover could not clean its own panels, relying instead on occasional wind gusts to blow some of the dust away. For several years, these cleaning events occurred often enough to keep power levels adequate. Then Spirit became stuck in soft soil in May of 2009, unable to free its wheels despite months of effort by controllers on Earth. Its fixed position meant engineers could no longer angle the rover to tilt its dusty panels toward the sun during the approaching Martian winter. Solar power output dropped steadily as winter deepened, and the dust-covered panels absorbed less and less of the weakening seasonal sunlight. With declining power came declining heater budgets. Spirit could no longer keep all of its systems warm through the long, dark, -80-degree nights. Engineers prioritized the most critical components, allowing others to cool below their survival temperatures, accepting progressive damage to conserve enough power for the systems that might allow communication when spring returned. Spring came. Spirit did not respond. The most likely cause, based on engineering analysis, was that the rover's internal temperatures had dropped low enough during the winter to cause irreversible damage to critical electronics or wiring. The exact failure point was never identified, but the mechanism was clear. Reduced sunlight led to reduced power, which led to reduced heating, which led to temperatures dropping below the survival thresholds of components essential to the mission. A thermal power death spiral, the same pattern slowly ending the Voyager missions in interstellar space, played out on the surface of Mars in a single Martian winter, not from a sudden freeze, not from a dramatic failure, from the quiet, patient arithmetic of diminishing thermal margins. This pattern, the slow tightening of the gap between available heat and required heat, defines the engineering future of deep space exploration. And it is a pattern that depends entirely on one material, plutonium-238. Every radioisotope thermoelectric generator and every radioisotope heater unit that has ever flown in space has used plutonium-238 as its heat source. There is no operational alternative, and the global supply of this isotope is alarmingly limited. The United States stopped producing plutonium-238 in the late 1980s, and existing stockpiles have been depleted by decades of space missions. The Department of Energy restarted limited production at Oak Ridge National Laboratory, but output remains small, only about 1.5 kilograms per year, against projected demand that exceeds that figure for ambitious future missions. Without adequate plutonium-238, future deep space missions face a fuel crisis that is simultaneously a thermal crisis, because no plutonium means no heat source, and no heat source means no thermal survival beyond the reach of the sun. This is why NASA's January 2025 test at the Glenn Research Center in Cleveland, Ohio, drew quiet but significant attention from the deep space engineering community. In collaboration with the University of Leicester in the United Kingdom, NASA engineers successfully tested a Stirling generator powered by americium-241, a different radioactive isotope that is far more abundant than plutonium-238. Americium-241 is a byproduct of nuclear reactor operations and exists in stockpiles measured in hundreds of kilograms across Europe and North America. It produces less heat per kilogram than plutonium-238 and requires more shielding due to its gamma radiation emissions, making generators heavier. But it is available, and availability, when the alternative is having no heat source at all, changes the entire calculus of deep space thermal design. The Stirling converter technology used in the test also represents an improvement over traditional thermoelectric conversion. Instead of using solid-state thermocouples with efficiencies of 6 to 7%, Stirling converters use a small reciprocating engine driven by the temperature difference between the heat source and the cold radiator. Conversion efficiencies can reach roughly 25 to 30%, roughly 4 times better than thermoelectric systems. This means that a Stirling generator using americium-241 could potentially produce comparable electrical output to a traditional plutonium-fueled thermoelectric generator while using a fuel that is orders of magnitude more available. The test at Glenn demonstrated that the americium heat source simulators could sustain Stirling converter operation within expected performance parameters, and critically, that the system could survive the failure of one converter without losing power entirely, a crucial reliability requirement for missions where repair is impossible. This test does not solve the deep space thermal problem. Americium-fueled generators are heavier, have not yet flown in space, and require further qualification before any space agency will commit a mission to them. But they represent a possible answer to a question that has loomed over deep space exploration for decades. When the plutonium runs out, what keeps the spacecraft warm? If americium works, the answer is something that exists in supply rather than scarcity. If it does not, every future mission beyond Jupiter faces a thermal dead end that no amount of insulation or clever engineering can overcome. The vulnerability of specific spacecraft systems to cold deepens the danger as missions push farther from the sun. Batteries are among the most thermally sensitive components aboard any vehicle. Lithium-ion cells, the standard for modern spaceflight, perform optimally at room temperature but lose capacity as they cool. At -20 degrees Celsius, a typical lithium-ion cell retains roughly 80% of its room temperature capacity. At -40 degrees, capacity can drop below 50%. Below -50 degrees, many lithium-ion chemistries suffer permanent internal damage as lithium metal plates onto the anode during charging, creating irreversible capacity loss and potential internal short circuits. Keeping batteries warm enough to function requires dedicated heaters, and those heaters draw power from the very batteries they are protecting, creating a circular dependency that can become fatal if the thermal balance shifts even slightly in the wrong direction. Propellant systems face equally severe thermal challenges. Hydrazine, the most common monopropellant used for spacecraft attitude control and small maneuvers, freezes at approximately 2 degrees Celsius. This is not a deeply cryogenic temperature, it is barely below room temperature by earthly standards. But in a spacecraft where every watt of heating power is precious, and where propellant lines can run through shadowed structural areas far from any heat source, keeping hydrazine liquid requires constant thermal vigilance. A frozen propellant line does not merely prevent a thruster from firing, it creates a blockage that can trap pressure, distort tubing, and crack fittings. Even if the line is eventually rewarmed, the mechanical stress from repeated freezing and thawing may have already compromised the system's integrity. Bipropellant systems using combinations like monomethylhydrazine and nitrogen tetroxide face similar constraints, with freezing points and thermal sensitivity ranges that demand precise temperature management throughout the mission. Cryogenic propellants, the liquid hydrogen and liquid oxygen that provide the highest performance for large orbital maneuvers, represent the extreme end of this challenge. Liquid hydrogen boils at roughly -253 degrees Celsius. Liquid oxygen boils at -183 degrees Celsius. Storing these fluids in space requires keeping them at cryogenic temperatures indefinitely against the relentless trickle of heat leaking through insulation, conducted through structural supports, and radiated from warmer spacecraft components. Even the best multi-layer insulation cannot reduce heat leak to zero. Conservative estimates for current passive storage technology suggest boil-off losses of roughly 0.5% of total propellant mass per day. Over a 4-month transit to Mars, that translates to losing more than 40% of the initial fuel load to evaporation. For longer missions to the outer solar system, the losses would be effectively total. The propellant would simply boil away before the spacecraft arrived at its destination. NASA has been developing zero boil-off technologies, active cryocooler systems that intercept and remove the heat leaking into propellant tanks. But these systems require electrical power, add mass and complexity, and introduce additional failure modes. As of the mid-2020s, no spacecraft has yet demonstrated long-duration cryogenic propellant storage in deep space. Thermal cycling inflicts a different kind of damage, one that accumulates silently over months and years. In the inner solar system, a spacecraft in low orbit passes from sunlight into shadow and back every 90 minutes. Each transition subjects the external structure to a temperature swing of roughly 200 to 300 degrees Celsius. Materials expand when heated and contract when cooled. Metals, polymers, adhesives, solder joints, and composite layups all expand and contract at different rates, creating mechanical stress at every interface where dissimilar materials are bonded together. Over thousands of cycles, these stresses fatigue the materials. Micro cracks propagate, adhesive bonds weaken, Solder joints develop hairline fractures that increase electrical resistance and can eventually cause open circuits. Polymer films embrittle as their molecular chains break under the combined assault of thermal cycling, ultraviolet radiation, and charged particle bombardment. The degradation of insulation materials on the Hubble Space Telescope was driven in large part by this thermal cycling mechanism, but Hubble orbits in the relatively benign thermal environment of low Earth orbit. Spacecraft operating in more extreme environments face amplified versions of the same problem. A probe orbiting close to the Sun experiences more intense heating during illuminated passes. A probe in the outer solar system experiences colder shadow temperatures, increasing the amplitude of the thermal swing, and probes in elliptical orbits, which travel from close solar approaches out to deep space distances and back, experience the widest thermal swings of all, subjecting their structures to the full range of the solar system's thermal extremes. Mechanical joints and moving parts are particularly vulnerable. Lubricants formulated for operation at room temperature can thicken, stiffen, or freeze entirely at deep space temperatures. A reaction wheel bearing lubricated with conventional oil may spin freely at 20 degrees Celsius, but seize at -80 degrees as the oil becomes too viscous to allow rotation. Specialized low-temperature lubricants exist, but they often sacrifice performance at higher temperatures or have shorter operational lifetimes, forcing engineers into trade-offs between cold survivability and warm condition performance. Seal materials face similar constraints. Elastomeric O-rings and gaskets that provide reliable sealing at moderate temperatures can harden and shrink at extreme cold, opening gaps that allow fluid leaks or atmospheric escape. The Space Shuttle Challenger disaster of 1986, while not a deep space thermal event, demonstrated with tragic clarity how cold, stiffened O-ring seals can fail catastrophically when temperatures drop below their design qualification range. Electronics add yet another dimension to the vulnerability map. Semiconductor devices generally function well at cold temperatures, and in fact many electronic noise sources decrease as temperature drops, which is why some astronomical detectors are deliberately cooled to cryogenic levels for maximum sensitivity. But the supporting components around those semiconductors, the capacitors, resistors, solder joints, wire bonds, and circuit board substrates, have their own thermal limits. Electrolytic capacitors contain liquid electrolyte that can freeze at very low temperatures, causing the capacitor to lose its function entirely and potentially cracking its housing when the electrolyte expands. Crystal oscillators, which provide the precise timing signals that synchronize every digital system aboard a spacecraft, shift frequency as temperature changes. If the oscillator drifts too far from its nominal frequency, communication protocols break down, data becomes corrupted, and command sequences fail to execute properly. The cumulative picture that emerges from examining these individual vulnerabilities is stark. A deep space spacecraft is not a simple object surviving in a cold environment. It is a collection of thousands of components, each with its own thermal survival range, each depending on the thermal control system to maintain it within that range, each capable of cascading failure if it drifts outside its limits. A frozen propellant line does not just disable a thruster, it can prevent the spacecraft from orienting itself, which can point a radiator at the sun instead of cold space, which can cause the cooling system to lose effectiveness, which can cause electronics to overheat on one side of the vehicle while other components continue freezing on the opposite side. A failed heater on a battery does not just reduce battery capacity, it can limit the power available to run other heaters, which can allow additional components to cool below their limits, each failure enabling the next in a tightening spiral. Engineers call this thermal cascade, and it is the nightmare scenario that drives every aspect of deep space thermal design. No single component failure should be capable of triggering a chain reaction that kills the spacecraft. Redundant heaters, backup fluid loops, independent power buses, and fail-safe thermostatic controllers are all designed to prevent any single thermal event from propagating into a system-wide collapse. But redundancy has limits. Every backup heater draws power from the same shrinking generator. Every redundant fluid loop adds mass, complexity, and potential leak points. Every fail-safe controller requires sensors and wiring that are themselves vulnerable to thermal extremes. At some point, the margins become thin enough that a single unexpected failure, a heater that degrades faster than predicted, a seal that embrittles sooner than tested, a battery that loses capacity more sharply than the thermal model assumed, can begin the cascade. And the farther you travel from the sun, the thinner those margins become. Near Earth, solar energy provides a generous thermal backstop. Even if a heater fails, the sunlit side of the spacecraft still absorbs substantial warmth, and the abundant electrical power from solar arrays allows engineers to reroute current to backup heating circuits. At Jupiter, the backstop weakens dramatically. At Neptune, it effectively vanishes. Beyond the Kuiper belt, there is no backstop at all. Every watt of thermal energy the spacecraft possesses comes from its onboard generator, and that generator's output is fixed, declining, and finite. This is the reality that transforms the cold of deep space from a simple number on a thermometer into an engineering challenge of almost existential difficulty. The danger does not arrive as a dramatic wall of cold slamming into the hull. It arrives as arithmetic, as the slow, relentless subtraction of available power from the thermal budget, watt by watt, year by year, pushing every system closer to the edge of its survival range while offering no external source of replacement warmth. The sun, which near Earth provides more thermal energy than any spacecraft can use, becomes a memory. A bright point in the sky, a reminder of the warmth that once made thermal management a matter of redirecting abundance rather than rationing scarcity. And when that scarcity finally catches up with the engineering, when the generator's output can no longer sustain both the instruments that justify the mission and the heaters that keep the vehicle alive, the spacecraft does not die in a single dramatic moment. It dies the way the Voyagers are dying right now, one system at a time, one heater switched off to save power for another, one instrument allowed to cool beyond its limits in hopes that it will survive a little longer, one thermal margin erased after another until the cascade finally begins and nothing remains to stop it. The question that remains, the question that transforms this engineering challenge into something genuinely terrifying, is what that cascade actually looks like from inside. What fails first? What fails next? And why the answer reveals that deep space cold is not merely worse than most people think. It is worse in ways that most people have never even considered. Begin with a single valve, a small one, tucked behind a structural panel in the propulsion module of a crude deep space habitat, somewhere beyond the orbit of Mars, where the sun has shrunk to a fierce bright point delivering less than half the solar energy available at Earth. The valve controls the flow of hydrazine through a thruster feed line. It is a simple mechanism, a spring-loaded poppet seated against a metal housing, sealed by a polymer gasket designed to remain flexible across a temperature range of -40 to +70 degrees Celsius. An electric heater strip bonded to the valve body with thermally conductive adhesive keeps the assembly above -10 degrees Celsius by cycling on and off every few minutes under thermostatic control. The heater draws 11 watts. It has been cycling faithfully for 14 months. Then the thermostat fails. Not dramatically. Not with a spark or a warning alarm. The bimetallic sensor element inside the thermostat, which has flexed tens of thousands of times through 14 months of on-off cycling, develops a fatigue crack at its brazed joint. The crack opens a gap of a few hundredths of a millimeter, just enough to change the electrical resistance of the circuit. The thermostat now reads a temperature approximately 8 degrees warmer than the actual valve body temperature. It believes the valve is at -2 degrees Celsius when the valve is actually at -10. It does not call for heat. The heater stays off. For the first hour, nothing visible happens. The valve body is a chunk of stainless steel with substantial thermal mass. It cools slowly, radiating heat into the surrounding structure at a rate governed by the modest temperature difference between itself and the shadowed panel behind it. After 3 hours, the valve body has dropped to -18 degrees Celsius. The polymer gasket has stiffened noticeably. Its shore hardness has increased by roughly 30%, and its elastic recovery has diminished. It no longer conforms perfectly to the sealing surface. A micro gap has opened at the interface, too small to allow measurable propellant leakage, but large enough to change the valve's response characteristics. If commanded to open, the valve might stick briefly before releasing, introducing a delay of perhaps 50 milliseconds into what should be an instantaneous actuation. After 8 hours, the valve body temperature has passed -25 degrees Celsius. The hydrazine in the feed line immediately upstream of the valve, a section roughly 30 centimeters long that shares thermal contact with the valve body through a brazed fitting, has cooled below its freezing point of approximately 2 degrees Celsius. A plug of frozen hydrazine now blocks the line. The thruster served by this line is inoperable. The spacecraft has lost one of its attitude control thrusters, not from a collision, a software error, or a design flaw in the thruster itself, from a cracked thermostat on a heater strip attached to a valve that nobody was monitoring at that moment, because every other telemetry channel on the vehicle reported nominal. This is where the cascade begins. The flight computer, detecting that one thruster has failed to respond to a routine attitude maintenance command, switches to a backup thruster configuration. This configuration uses a different set of thrusters on the opposite side of the vehicle to maintain orientation. The new thruster geometry works, but it applies slightly different torques that result in a marginally different steady-state attitude. The spacecraft's orientation shifts by less than 2 degrees. Under normal circumstances, this would be a trivial adjustment, well within the pointing tolerance of the communications antenna and the thermal radiator panels. But the radiators on this vehicle are optimized for a specific orientation relative to the sun. They are designed to face the cold anti-solar sky, maximizing the temperature difference that drives infrared heat rejection. A 2-degree attitude change rotates the radiator array, so that a portion of its surface now catches a sliver of direct sunlight. The effect is initially small. The radiator's heat rejection capacity decreases by roughly 3%, as the illuminated area absorbs solar energy instead of emitting thermal infrared. But 3% of the total cooling budget, on a vehicle operating far from the sun with thin thermal margins, is not trivial. The internal thermal control loop, which circulates coolant between the habitat module's electronics racks and the external radiators, begins running slightly warm. Coolant return temperature rises by 1.5 degrees Celsius. The environmental control system compensates by increasing coolant pump speed, which draws additional electrical power from the vehicle's generator. Meanwhile, the frozen propellant line has created a secondary problem. The hydrazine plug, now solidly frozen, has contracted at a different rate than the surrounding metal as temperatures continue dropping. This differential contraction has stressed the brazed fitting between the valve body and the feed tube. The fitting has not cracked. Not yet. But the mechanical preload on the joint has changed, and when the spacecraft later performs a planned thermal cycle, warming this section of the structure during a scheduled propulsion system checkout, the differential expansion between the frozen hydrazine plug and the surrounding metal will impose a transient stress that approaches the fitting's fatigue limit. Each subsequent freeze-thaw cycle, if the heater is eventually repaired or the thermostat failure is diagnosed and corrected, will accumulate damage at this joint. The fitting may survive another 100 cycles, or 10, or 1. Inside the habitat module, the crew notices nothing. Their living space is maintained at a comfortable 22 degrees Celsius by the environmental control and life support system, a network of air handlers, heat exchangers, humidity separators, and carbon dioxide scrubbers that together consume roughly 2 kilowatts of electrical power. The cabin air circulates through ducted fans, because in microgravity there is no natural convection. Warm air does not rise. Cool air does not sink. Without forced circulation, an astronaut sleeping in a still corner of the module would exhale carbon dioxide that would form a stagnant bubble around their face, slowly displacing the oxygen they need to breathe. The fans prevent this by maintaining continuous airflow past every surface, through every rack, around every sleeping station. The air passes through a condensing heat exchanger that removes both excess heat and humidity, pulling water vapor from the cabin atmosphere and depositing it as liquid condensate for recycling. This condensate collection system is itself thermally sensitive. The heat exchanger surfaces must be cold enough to cause condensation, but warm enough to prevent the collected water from freezing on the plates, which would block airflow and shut down humidity control within hours. The crew trusts this system because it works. It has worked every day for 14 months, but every component in the chain carries a temperature specification, a narrow window between too hot and too cold, and those windows are maintained by the same thermal control architecture that is now running slightly warm because a radiator caught a sliver of sunlight, because a thruster configuration changed, because a propellant valve froze, Because a thermostat cracked. This is the anatomy of a thermal cascade, and it is the reason that the cold of deep space is worse than most people have ever considered. The danger is not a single catastrophic freeze. It is the interconnectedness of thermal systems in an environment that provides no buffer, no forgiveness, no natural mechanism for correcting imbalances. On Earth, the atmosphere serves as an enormous thermal buffer. It absorbs excess heat during the day and releases it slowly at night. It carries warmth from equatorial regions toward the poles. It provides a medium through which heating systems, cooling systems, and living bodies can all exchange thermal energy with minimal engineering. In deep space, this buffer does not exist. Every thermal interaction must be deliberately engineered. Every watt of heat must be moved through designed pathways. Every component's temperature depends on a chain of thermal connections that ultimately leads to either the onboard power source or the radiators facing the void. Break any link in that chain, and the component's temperature begins drifting toward whatever equilibrium the remaining connections can sustain. If that equilibrium lies outside the component's survival range, the component fails, and its failure changes the thermal landscape for everything connected to it. Consider the water systems inside a crude deep space habitat. Water is used for drinking, food preparation, hygiene, cooling, oxygen generation through electrolysis, and humidity control. It circulates through pipes that thread through every module of the vehicle, crossing structural interfaces, passing through walls, running alongside electrical cables and data lines. In a properly heated habitat, water flows freely through these pipes at temperatures between roughly 5 and 40 degrees Celsius. But water freezes at 0 degrees Celsius. Not at -50, not at -100, at 0. A propellant line carrying hydrazine has a freezing point just 2 degrees above that. Water and hydrazine, the two most common fluids aboard a crewed spacecraft, freeze at temperatures that exist routinely on the cold side of any thermal gradient in space. A water line that passes through a poorly insulated section of the habitat's structure, perhaps crossing a joint where two modules connect, or running behind a panel that faces the anti-solar side of the vehicle, is vulnerable to localized freezing, even when the rest of the water system operates normally. The thermal environment at that specific point, determined by the local balance of heater input, conductive heat flow from adjacent warm structures, and radiative loss to colder surroundings, may hover just a few degrees above freezing under normal conditions. A reduction in heater power, a shift in vehicle attitude that changes the local radiation geometry, or an increase in heat loss from a nearby insulation defect can tip that local balance below the freezing point. Ice forms in the pipe. Flow stops. The blockage prevents coolant from reaching a downstream heat exchanger. The heat exchanger warms up. The equipment it serves warms up. Somewhere in the habitat, a processor or a power converter begins exceeding its maximum operating temperature, while somewhere else, in the section cut off from coolant flow, components are getting colder because the now stagnant fluid is no longer carrying warm water from the heated core. The spacecraft is simultaneously too hot and too cold in different places for different reasons, all traceable to a single frozen section of pipe. And the crew, floating in their comfortable 22-degree cabin, may not realize the severity of the situation until warning alarms begin cascading across their displays, each one a symptom of the same underlying thermal fracture. Batteries compound the vulnerability. Every deep space vehicle carries batteries to provide power during periods when the primary generator is insufficient to meet peak demand or to serve as emergency backup in the event of a generator anomaly. Lithium-ion batteries, the current standard for human spaceflight, are thermally needy. They charge efficiently and deliver their rated capacity at room temperature. At -20 degrees Celsius, they retain roughly 80% of their capacity. At -40, they drop below 50% and risk permanent damage from lithium plating during charging. A battery pack that loses its dedicated heater, or that is thermally connected to a section of structure experiencing unplanned cooling, can slide into a state where it lacks the capacity to power the heaters that would keep it warm. This circular dependency, where the component needs heat to function and needs to function to produce the power for heat, is one of the most insidious failure modes in deep space thermal design. Engineers build in margins to prevent this loop from closing. They size battery heaters conservatively. They provide redundant heating circuits. They position battery packs in thermally favorable locations near the core of the vehicle, but margins erode with distance from the sun, with generator age, with accumulated insulation degradation, with every year of thermal cycling that weakens adhesive bonds and fatigues heater wiring. Eventually, the margin between a functioning battery and a dead one becomes narrow enough that a single coincidence, a heater controller glitch during a shadow pass, a brief attitude excursion that shifts the thermal environment, can push the battery below its survival threshold. The electronics aboard a deep space vehicle present a paradox that makes thermal management even more fraught. Most electronic components generate waste heat when they operate, and many require active cooling to prevent overheating. But the same components, when powered off, must be kept above minimum storage temperatures to prevent damage to solder joints, capacitor electrolytes, and semiconductor packaging. A powered computer generates enough waste heat to keep itself warm, but a computer that's been shut down to conserve power immediately begins cooling toward the ambient temperature of its surroundings. If that ambient temperature is minus 40 degrees Celsius, because the computer is mounted in a section of the vehicle with limited heater coverage, the computer may cool below its minimum storage temperature before it can be powered up again. Restarting it in that state risks cold start failures, cracked solder joints, or capacitor malfunction. The engineer who shut the computer down to save 11 watts of power may find that restarting it is no longer possible, not because the computer broke, but because the thermal window for safe startup has closed. Seals and gaskets, the quiet guardians of atmospheric integrity, face their own cold-driven reckoning. A crude habitat in deep space contains approximately 1 atmosphere of pressurized air, the same air pressure found at sea level on Earth, held inside a thin-walled metal shell surrounded by the vacuum of space. The only thing preventing that atmosphere from explosively escaping is the structural integrity of the pressure vessel and the sealing performance of every hatch, port, window, feed-through, and joint in the habitat's hull. Many of these seals are made from elastomeric materials, synthetic rubbers and silicones chosen for their flexibility, resilience, and ability to conform to imperfect mating surfaces. These materials perform beautifully at moderate temperatures. At extreme cold, they harden. Their flexibility decreases. Their ability to recover from compression diminishes. A seal that provides a perfect gas-tight barrier at 20 degrees Celsius may develop microleaks at minus 30 degrees as the elastomer contracts away from the metal sealing surface. In a well-designed habitat, these seals are protected by heaters and insulation. But in a thermal cascade, where heater power is being diverted to higher priority systems and insulation performance may be degraded by years of thermal cycling and radiation exposure, the seals become one more vulnerability in a chain of interdependent thermal risks. The psychological dimension of this thermal fragility adds a burden that no engineering analysis can fully capture. A crew inside a deep space habitat lives in constant proximity to an environment that will kill them if the thermal control system fails comprehensively. They eat, sleep, work, and exercise inside a pressurized volume maintained at a livable temperature by machines that are always running, always consuming power, always rejecting heat through radiators that must face the right direction, always circulating fluids that must not freeze, always cycling air through exchangers that must not ice over. Every system they depend on for survival, atmosphere, water, food storage, waste processing, medical equipment, communications, has a thermal operating range, and those ranges are maintained by an interconnected web of heaters, coolant loops, insulation, and controllers that share the same finite power supply. On the International Space Station, orbiting less than an hour from Earth by emergency re-entry timeline, a thermal control failure is a serious but recoverable emergency. The crew can shelter in a different module, seal off the affected section, and wait for ground controllers to diagnose and correct the problem. Replacement parts can be launched from Earth within weeks. In the worst case, the crew can evacuate to a docked spacecraft and return home. In deep space, none of these options exist. A crew at Jupiter distance is 40 to 50 minutes of light travel time from Earth in each direction, making real-time communication with ground controllers impossible. A crew in transit between planets cannot dock with a supply ship. A crew beyond Mars has no emergency return option measured in days or weeks. They are committed to their vehicle for months or years. and the vehicle's thermal control system must work for the entire duration, without resupply, without repair from external teams, and without the generous solar energy that makes near-Earth thermal management comparatively forgiving. This is what makes the cold of deep space worse than you think. It is not worse because the temperature is lower than you imagined. It is worse because the environment offers nothing, no warmth, no air, no thermal buffer of any kind, to help you survive. Every degree of warmth inside a deep space habitat is manufactured warmth, produced by a generator fueled by radioactive material that decays on its own schedule regardless of how desperately you need its heat. Every degree of cooling is manufactured cooling, achieved by radiators that only work if they face the right direction and if their coolant has not frozen in the lines. Every component, every fluid, every seal, every living body aboard the vehicle exists inside a temperature range maintained entirely by engineering, and that engineering must function perfectly, continuously, for years, with declining power, accumulating damage, and no possibility of external rescue. The conclusion is not the one Hollywood has prepared you for. The cold of deep space is not a monster lurking outside the hull, waiting to burst through and freeze the crew in their bunks. It is not an attacking force that can be defeated by thicker walls or more powerful heaters. It is something stranger and more unsettling than that. It is an absence. The absence of a forgiving environment, the absence of atmosphere, the absence of convection, the absence of any medium that naturally moves heat from where it is abundant to where it is needed. On Earth, the environment does enormous thermal work for free. Air carries warmth from your furnace to every room of your house. Water distributes solar heat across ocean currents spanning thousands of kilometers. The atmosphere moderates temperature swings between day and night, between summer and winter, between sunlight and shadow. None of this exists in space. In space, heat goes nowhere unless you build a path for it. It stays where it is generated unless you pump it somewhere else. It accumulates where it is unwanted unless you radiate it away through panels facing the void. And it drains from where it is needed unless you replace it, watt by watt, from a source you carried with you. A spacecraft in deep space is an artificial world, a closed bubble of engineered habitability drifting through an environment of absolute thermal indifference. The void does not care whether the crew is warm. It does not care whether the propellant is liquid. It does not care whether the batteries are charged or the seals are flexible or the water is flowing. It simply exists, 3 degrees above absolute zero, offering nothing and taking nothing except the infrared radiation that every warm surface emits, whether anyone wants it to or not. Survival in this environment means maintaining a thermal balance so precise, so continuously managed, so dependent on the correct functioning of interconnected systems, that the failure of a single 11-watt thermostat can initiate a sequence of events that threatens an entire mission. The Voyager spacecraft, drifting through interstellar space on dwindling power, shutting down one heater and one instrument at a time, are not relics of a past era. They are a preview of the fundamental challenge facing every future mission that ventures beyond the comfortable warmth of the inner solar system. Every crewed mission to Mars, every proposed outpost at the lunar South Pole, every conceptual voyage to the moons of Jupiter or Saturn, every interstellar probe humanity might one day launch toward another star. All of them will face the same physics. All of them will fight the same invisible war. The war to keep heat where it is needed and remove it where it is deadly, in a universe that offers no natural assistance with either task. The cold of deep space is not terrifying because it freezes everything instantly. That would be simple, that would be dramatic, that would be a threat you could understand in the time it takes to watch a movie. The cold of deep space is terrifying because it does not freeze everything instantly. It waits, it is patient. It works through gradients and margins and slow arithmetic, through declining generator output and accumulating insulation damage and the steady creep of thermal boundaries toward the survival limits of components that were never designed to last forever. It does not attack the ship from outside. It erodes the ship from within. 1 watt at a time, 1 degree at a time, 1 failed thermostat at a time, until the fragile thermal balance that separates a living spacecraft from a frozen monument can no longer hold. Far from the sun, in the vast emptiness between worlds, heat is not a resource you can take for granted. It is the most precious commodity aboard any vehicle, more valuable than fuel, more critical than oxygen, more fragile than any instrument. Lose control of heat, even briefly, even locally, and the cascade begins. And in deep space, where no star warms your hull and no atmosphere carries your waste heat away, there is nothing outside the walls of your small artificial world that will help you stop it. That is what makes the cold of deep space worse than you think. Not the number on the thermometer, not the distance from absolute zero, not the Hollywood image of a crew frozen solid in their chairs. It is the knowledge that everything, every breath of warm air, every degree of comfortable temperature, every drop of liquid water, every functioning circuit and every flexible seal and every watt of power keeping the batteries alive exists only because a machine is maintaining it. And the machine runs on finite fuel in an infinite void that offers nothing in return except the cold, patient, indifferent dark.